Hello everyone. So today we're going to go and talk about molecule polarity. So this is polarity of molecules with one atom, two atoms, or I'm sorry, just two atoms and three atoms. This is basic polarity. I'm going to go and explain. Um, you will use this information for intermolecular forces when we learn about that, which will be coming up actually. We've started that last Thursday. So um, yeah, anyway. Uh, so if you guys are confused about polarity, I'm going to go and talk about that in this video. I am going to be using a simulation. The simulation is from a program of University of Colorado Boulder called PhET, spelled P-H-E-T. They make great simulations. Over 275 million simulations have been delivered by these people. They make a lot of simulations. They're pretty awesome, guys. They're free, so I've been playing with these all my life to kind of figure out, not all my life, all my college life and some of high school, where you kind of learn about chemistry in an interactive way. So this is one way that I can actually deliver course content to you guys in a more visual manner. If you people are visual learners, if you're not and you learn through a book, we'll read the book. Anyway, so for this video, like I said, polarity, we're gonna go and look at dipole moments, partial charges, and a little bit of bond character, which is simply whether or not this molecule is more covalent versus ionic, et cetera, et cetera. We're going to also look at an electrostatic potential. This essentially is just like, I'll even show you. It's just this like weird colorful thing. This basically is what you'll see on a lot of Dr. Van Doren's PowerPoint slides. You'll see this more in real life. Basically, this is what we see in terms of negativity versus positivity of charges. You won't be tested on this stuff. You won't be tested on this stuff. However, it's good to kind of know this in terms of the fact that we look at them on PowerPoint slides. You might as well know it. Anyway, so we have two atoms here. They are vague. They are not actual atoms from a periodic table. This is atom A and atom B. Now, atom A is not very electronegative. Atom B, however, I'm going to crank up the electronegativity, and you're going to see what happens in terms of the bond dipole. This arrow is very tiny. I only changed it a little bit, so it's still not very electronegative. So basically the dipole here is very tiny. It's not that great and not really that polar. It's still a little polar, but not super, super polar. The polarity simply means that one atom is more electronegative than the other, and it's winning in this tug of war of electrons, valence electrons. The more electronegative I make it, see how there's actually a bond character now? There's actually this really strong dipole where this is positive, right? This is why the little plus on the arrow looks like a plus, and it's going in this direction, and this is partially negative. Partial negatives are different than actual negative charges. Those are different. Negative charges mean that you have extra atoms. Partial negatives mean this is more electronegative. So charges versus negativity, what is that? Well, if I'm charged negative, that just means I have extra electrons. Partial negativity means I want a lot of electrons. Not that I have them, but I really, 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 I'm electron hungry. And we'll talk about what those are called in 101B, but some of those are called electrophiles. We don't really care about that at the moment. However, if you've heard of it, awesome. If not, good. You don't really need to worry about that yet. However, just know that partial negatives mean that I'm really electron hungry. I will win in terms of when it comes to a tug of war between electrons. I will win because I'm starving. Versus this partial positive where this atom is not very electronegative. It's not going to really hold on to the electrons too much because it can't. It'll actually just let go of it. That's why the bond dipole goes in this direction. It goes in this way. Bond character just means that the more electronegative one atom is to another, the more ionic you are. Simply because if you look at something like NaCl, just think of it like this. This is Na and this is Cl. One is very low in electronegativity. It's on the other side of the periodic table versus Cl, which is on the other side, it's on the more electronegative side. The more electronegative you are, the more ionic and bond character you have. Although, be sure to remember that ionic bonds are a whole transfer of electrons. I'm not sharing electrons anymore. I'm actually giving one away. And I'm bonded that way. Versus covalence, where we're actually sharing bonds. So do know the difference. If you're polar, that doesn't mean that you're an ionic bond. That just means I have more ionic character, and that's what we call this bond character. In terms of electrostatic potential, see how we're more red on this side? That pretty much basically just means that I'm more negative. It's the same thing as saying I'm partially negative. We look at partial negativity more. This one right here that's blinking. We look at that more. That's important to know what's partial negative. Now, it's really easy to show with 2 atoms. Let's go to 3 atoms. So I have, oops, this is weird. I have atom A, B, and C. I'm going to make B the most electronegative here. When I do that, see how the bond dipoles, essentially A and B are being pulled. So B is pulling A and it's pulling C as well. Basically, the molecular dipole, so bond dipoles are going towards B. The full molecular dipole is actually going in this direction. And this is part of that vector addition that Dr. Van Dorn was doing. Basically, think about it as 3 groups of your entire family during a family reunion are having a tug of war. And B is winning. If B is winning and pulling in this direction, basically A is not going to be over here and C is not going to be over here. They're all going to go with B in this direction. That's it. Partial charges, B is very partially negative versus A and C, which are partially positive. That's really it. Now, if I'm gonna go and decrease atom B's electronegativity, I'm gonna increase atom C's electronegativity. Do you see how when I increase atom C's electronegativity, the bond dipole between A and B does not change because I'm not messing with A or B. I'm actually messing with atom C. So the bond dipole between B and C are now decreasing, as you see in strength. It's getting smaller and smaller. At the same time, because I'm changing that, my full molecular dipole is also changing. So if I keep doing this, see how at a certain point my bond dipole reversed so that C was more electronegative because I passed the point of electronegativity of B. If I keep it the exact same, basically no one's winning. See, there's no more arrow. No one's winning. So B and C are equally electronegative, and B is the one pulling A. C is not pulling A because it's not bonded to A. So B is essentially pulling A, so the molecular dipole goes in this direction. Nothing else is being pulled. These two are pulling each other at the same exact force. Careful with the word force. They're pulling each other at the exact same intensity, so they cancel each other out. Basically, is what's happening. However, I'm going to go and increase it more and more and more. So it's a little strange. So B is pulling C at a great intensity. So is B is pulling A. So C is pulling B, B is pulling A. The fact of the matter is that we're no longer going to go, we're not going this way and we're not going this way anymore. Our full molecular dipole is going in the horizontal direction simply because of the thing we call vector addition. If you get what vector addition is, cool, you can use it. If not, don't really worry about it. The point of all this is essentially to be, asking, okay, well, if I have everything the same electronegativity, if I just increase all of it, we cancel each other out. So basically there's no polarity, which means this molecule is not polar. However, if one or more, depends on what the atom looks like, because if you have something like a tetrahedral, that's different. If I make one of these non-polar, at that point we have a dipole moment. We have a molecular dipole direction. We have bond dipoles. So you have to look at which one's more electronegative, draw out these dipoles, write what's partially positive versus partially negative. I could make this one partially, partially negative. Same thing, write those, and basically write where the molecular dipole's going. If we look at real molecules, let's look at hydrogen cyanide. This is a very basic one that we've looked at many times. It was on your worksheet for your the Lewis structure worksheet. So the bond dipoles, basically, hydrogen is not very electronegative. Nitrogen is. So is carbon. So carbon's going to pull H. I'm just going to predict this. Carbon's going to pull H, and nitrogen's going to pull C. If we look at the molecular dipole here, that's exactly what's happening. Whoops, this is weird. So if you guys can see this, sorry, I know it's a little strange. I'm going to zoom in for you. So if you guys can see this real quick, carbon is pulling hydrogen, as you can see by this little arrow. And if you look here, I know it's really hard to see, I am sorry, but basically this gray arrow right here, nitrogen is pulling carbon. So basically, and we look at the partial charges, these have values. Don't really worry about the values too much. You look at the electronegativities. I'm not sure if this chart's given to you on the exam, but you could use it for all the fun it is. If you look at the electronegative potential, or even the electrostatic potential, there's more electrons on this side. Basically because the entire molecule, this is the dipole, this is where most of the electrons, this is the electron-rich area, and the electron poor area. And this part right here is like neutral. It's where it has electrons but doesn't have a lot of electrons. So I'm gonna go and get rid of that. Let's look at another one. Let's look at water. Water's a fun one. So basically, oxygen is pulling both hydrogens. Don't worry about the actual numbers here. But if you could see where these arrows are going, the bond dipoles are going towards oxygen, and the molecular dipole going straight up. We've seen that before. Let's look at something like difluoromethane, CH2F2. This is a tetrahedral, right? Because carbon's the central atom, and we have two H's and two F's. So it is a tetrahedral. Oops, sorry. My computer just had a seizure. Notice how... Oh my god, my computer's being stupid. Notice how the dipoles here, I know they're a little weird and kind of hard to see, but basically the hydrogens are being pulled by the carbons. They're going towards the carbons, and these two fluorines are pulling this central carbon. So your molecular dipole's going straight up. We could look at partial charges if we want to. Not really that, huge. But basically know that with a tetrahedral, you're not flat like we see a tetrahedral on paper. This is different. Basically, one of them, that's where we see the whole wedge dash thing, but don't worry about that. Just know that with polarities, if you have something like this where you have two different atoms versus two other atoms on a tetrahedral, like two fluorines versus two hydrogens, the more electronegative atom, which is here the fluorine, will win. And that's what's going to be pulled with this difluoromethane. If we look at something else, like let's say ozone. Ozone has a dipole moment. Look at that. It's not canceled out like you would think. However, at the same time, you'd think it would be, because there's not really anything happening here except there is a bond dipole going in this downward direction. If we look at something like ammonia has an electron pair. That's why it looks trigonal, not trigonal planar, but trigonal pyramidal. If we look, nitrogen's pulling all of these things up, and therefore we have the molecular dipole going straight up. Basically, because we have a molecular dipole, these molecules are polar. I'm going to look at one more. Tetrafluoromethane. We see the bond dipoles, right? But we're missing the molecular dipole. See, it is checked, so if there is a molecular dipole, it should be showing. The thing is, it's not, because all the carbons are being pulled by this fluorine in the exact same intensity in all opposite directions. No one's winning. They're all pulling at the same strength because they're all electronegative, the same amount. Partial charges, see, they're all very electronegative, and not one fluorine is more electronegative than the other. So they're all pulling in the same intensity. No one's winning here. So there's no molecular dipole, which means this atom or this molecule is not electronegative. So hopefully that kind of helps you understand what polarity is. Basically, if you're not polar, you won't have a molecular dipole. You will have bond dipoles for sure, but all of them will cancel out, so you won't have a molecular dipole. I hope that's helped you figure out what polarity is. If you still have questions, put them in the comments below. Ask me. My name is Jay. Ask me during actually before or after class, or email me. You're free to ask during any office hours. Go see Dr. Van Dorn if you don't get this, or go see an SI session. Go see all the other preceptors. We all are here to help you. If you have any comments, compliments, suggestions for the videos, you're free to email me. My name is Jay. Please email me because I'm the one who makes the videos. No one else is responsible for this, so they won't know what you're talking about. Email me your suggestions. You can put them in the comments too if you're not shy. I applaud you for doing it. And feel free to ask your questions on the new Facebook page. You're free to do that as well. Thank you all for watching so much, and you guys have a good night.